All right, check one, check one. Lamai, can y'all hear me? Can y'all hear me properly and see me properly? Let me know quickly. All right, check one. Now, tell me if y'all can hear me properly. Right, again, hi, good evening, guys. Sorry, some people are asking for a Zoom link. I'm not actually doing the class on Zoom today. Okay, hi again. Um, good evening again. So, here's the deal. Y'all have just around, I think, 45 days, let's say 46 days till your exam, right? Y'all have less than 7 weeks. And starting today, we're going to do a series of, let's call it seminars, right? We're going to do a series of seminars and some classes for you all to like learn at least 90% of the syllabus, right? Also, I'm trying to do. Okay, so starting that, we're going to start with flip-flops today, right? So flip-flops is a part of your logic gates lesson, and it's a part that most of you don't really understand how it works, right? ඒක කොහොමද වෙන්නේ කියලා ලොකු අයිඩියා එකක් අත්‍තරම නැහැ. right? So after today's class, I actually hope that you all would get a proper understanding on what flip-flops are and how they work and how to write answers if those get asked for your exams, right? All right, let's begin. So here's the deal. Before we move on to before we move on to logical circuits, combinational circuits, sequential circuits, and flip-flops, right? Y'all gotta actually remember about logic gates properly. Hari. Logic gates, Gautama, there are 7 logic gates we had to talk about. What are those logic gates? I'll just put a brief thing here. Logic gates, we have NOT, we have AND, we have OR, we have NAND, we have NO, finally number 6, XOR or XO, finally XNOR or XNO, right? These are the 7 gates we have. So I hope you all kind of have an idea about these, right? Because I'm not going to waste any more time talking about these 7, right? So understand all the symbols, all the truth tables, and all the logics that they bring, right? For an example, for an XOR gate, the logic is that each time that we get an odd number of ones as the input, right? So in the inputs, if there's only an odd number of ones, the output will be 1, right? And for XNOR, it will be the quite opposite of it, right? AND gate says that if all inputs are turned on, the output will be turned on as well. The OR gate says that if even one of the inputs are turned on, the output will be turned on as well, and blah blah blah. All right, cool. So we're going to move ahead with logic circuits. I'm not going to waste a lot of time. This class will actually be around, let's say, 1.5 hours. Yeah, probably maximum of 2 hours. Okay. Logic circuits. A circuit is basically a combination of gates, right? We are using a bunch of gates in order to get one answer, right? It could have either one input or many inputs, right? But a circuit is essentially using a lot of logic gates to get one final output, right? Now, there are 2 different types of logic circuits, Lamai. Number 1 is the combinational circuits, and number 2 are the sequential circuits, right? So a combinational circuit is a circuit that depends on inputs, depends only on its inputs. But on the other hand, sequential circuits depend both on inputs and past states. Past states. ඒ කියන්නේ කලින් තිබ්බ විදියකුත් මතක තියාගෙන ඉන්නවා, right? Like with the input itself, input එකත් එක්ක එයා කලින් හිටපු විදිය තියෙන්නේ. ඒ විදියත් අරගෙන තමයි එයා දැන් output එක දෙන්නේ, right? Wait, give me a second. Oh, okay. Wait, the camera will be turned off just for a second. Okay, now it's back. All right, let's move on. Sorry. I'm looking for a way to get the quality into a higher part, but I can't seem to do it. Okay, for some reason, like, y'all are gonna be stuck with this resolution. It's a bit bad though. We'll see. Like, I'll try to do something after I let y'all write something. Okay? Right. So these are the two types of logic circuits we have. We have combination circuits only depending on its inputs, and sequential circuits that depends both on its inputs and past states as well, right? Let's take an example. Let's take an example like this. I'm going to tell you to do two things, right? I'm going to tell you to do two things. Number one is to raise your hand. Don't raise your hand, please, right? I can't even see. Number one is to raise your hand, and the number two is to let's do stand up, right? Raise your hand, and then command number two is to get up or stand up, right? There's two ways that you're going to tackle this question. Number one is that you're going to raise your hand, right? And when I tell you to get up, you're just going to get up, right? Your hand will be down, but you got up. What happened there? You took in the first input, you gave the output. You took in the second input, you gave the output to that, right? But on the other hand, there might be a child or a student that has their hand raised and got up while they have their hand raised as well. See what happens there? What happens is, he not only took in the input in the second one, right? He also remembered the past state as well. He remembers that he had his hand raised and he's going to get up with his hand raised. Get it? So those are the two combination circuits and sequential circuits, right? Now even in these categories, Lamai, for combination circuits we have two examples, like two proper examples, which are the half adder and the full adder, right? For sequential circuits, we obviously have flip-flops, which we are going to start right now. Okay, right. So with the parts that I told you all till now, do we have any questions? I don't think so, but do we? If you all have any questions, and if you do have my phone number, y'all can send me a WhatsApp text, or what y'all can do is y'all can like send a message in the YouTube chat as well. Okay. All right, let's move on. So, we're going to start with flip-flops now. Let me explain to you all what a flip-flop really is. So, in the most basic sense, Lamai, a flip-flop is a memory unit. Why? Because you remember something. Okay, a flip-flop is a memory unit, and it's the most basic memory unit there is. Okay, it's the most basic and the smallest memory unit there is. Now, in the memory hierarchy, the smallest memory unit that you all learn is the memory register, right? Usually a memory register can hold around 28 to 32 kilobytes of data, right? But while y'all are moving on with this, y'all will learn that a flip-flop can only hold 1 bit, like not even a KB, not even a byte, it's just 1 bit, either a 0 or a 1. That's all they can hold. Okay, right. Now here's how it's gonna go. When we are talking about flip-flops, Lamai, we have two main types of flip-flops, right? We have asynchronous flip-flops and synchronous flip-flops. These are the two that we are going to discuss today, right? There are many types of flip-flops. There's JK flip-flops, master-slave flip-flops. I think there's one called TK flip-flops as well, if I'm remembering correct, right? Those are not there for A-levels, right? For A-levels, you have two types of flip-flops, right? Those are called asynchronous and synchronous, right? What does asynchronous and synchronous means? Synchronous means that something has been synchronized with something, right? These are the two basic types. We have the basic flip-flops or the basic latches, as we call them, right? We call them a latch. Latch එකක් කියන්නේ holding on to something. හරිද? Holding on to something, right? Asynchronous. Then we have the clocked latches. I'll teach you what these are. These are the synchronous, right? Asynchronous and synchronous, right? So asynchronous means not synchronizing, and synchronous means synchronizing with something. We'll learn what the thing is later on, right? For the moment, we're going to talk about the basic latches, right? Now, talking about basic latches, Lamai, there are two types of latch flip-flops, right? There are two types of latch flip-flops, and number one is, hold on, yeah, there's not much ink here. Give me a second. Nah, it's fine. It's fine. It's fine. So there are two types of basic latches. Number one is the SR NAND flip-flop. It looks something like this. Okay, look straight. Right. Right. This is how a NAND flip-flop is drawn. We have S and R as the inputs. We have Q and Q bar or Q dash as the outputs. Right. This is how we draw a NAND flip-flop. Right. Now, it should be pretty easy, right? We take the inputs and we get the outputs. That's all. Hurry. Here's the tricky part. Now, imagine you want the answer for Q. You want the answer for Q, right? So you have one of the inputs, right? And the other input is actually Q bar, right? Meaning, in order for you to get Q, you need Q bar, right? So you go ahead and find the answer for Q bar and get it up, get it for Q, right? Easy, right? So you go for Q bar. Even for Q bar, there's one input ready, and the other input is actually Q, right? So it doesn't really make sense, right? In order for you to get Q, you need Q bar, and for you to get Q bar, you need Q, right? That's the entire situation here, right? In order for you to get this, you need this. To get this, you need this, right? That's where the wonderfulness of our universal gates come in, right? Now, we have our universal gate here, the NAND gate, right? So, this entire thing, this entire latch or the NAND flip-flop really depends on how a NAND gate works. It should, right? It actually should, okay? It only depends on, like bases on how a proper NAND gate works, right? Can you see the two? Yeah, you can. All right. So I'm going to draw a small NAND gate around here, and I'm going to draw the truth table for that NAND gate, right? Give me 2 seconds. Like, if y'all can just keep up with me, so we don't have to take much time, right? After I'm full with the board, like after I'm done teaching all the parts in one go, I'm going to give y'all like maybe 5 minutes to write everything down, okay? Right, so I'm gonna draw, yeah. So A and B is actually A dot B over bar, large over bar, right? For the truth table, so we have this, and here the outputs come as this. 0 and 0 is 0, but when you invert it, 1. 0, invert 1, 0, invert 1, 1, invert into 0, right? So here's how we usually draw a truth table for an AND gate, right? Right. Oh wait, I just realized why I don't have the best graphics. I haven't put my laptop to the charger. Hey, give me 2 minutes. Let me. Not even 2 minutes, just 30 seconds. Okay, now it'll start doing its magic. Okay. Yeah, everything will be better, right, graphics wise. Anyways, so here's how a normal NAND gate like truth table works, right? Look at this properly and try to understand what I'm trying to tell you, right? Every time that there's a zero in the inputs, the output is 1, right? Doesn't matter if it's 2 zeros, doesn't matter if it's 1 0. As long as there's a 0 in the inputs, the output is 1. Get it? So do we really need to look at both the inputs at once? No, right? In an AND gate, we don't need to look at both the inputs at once, right? We just look at one input, and if it's 0, we'll surely know that the answer is 1. That's a given, right? That's a given. If we have 0 as the input somewhere, it doesn't matter where, right? If we have 0 as the input, the answer should be 1. Get it? So this is the logic that we are going to use in order to solve this entire thing, right? Now, our final job is to make sure that we get the truth table for this, right? Meaning having 2 inputs and 2 outputs, right? Okay. Before that, before we get to the final truth table, I'm gonna do a random table actually. This is a random table. This is not a truth table, so don't worry because I'm gonna put inputs in many different ways here. Okay. We have S, we have R, we have Q, and we have Q bar, right? Okay, so here's what we're gonna do. I'm just gonna put 2 random inputs and see how to get an output, okay? For the moment, I'll put 0 and 1. Just for the, I don't know, just for the kick, right? Hitan nepa, don't think about it, right? I just put 0 and 1 as the inputs. Meaning, I'll use my red pen. We have 0 here and 1 here. Yes? Yes, right? We have 0 here and 1 here. Now, we're going to start using the logic that we just learned, right? If we have a 0, right? If we have a 0 here, it doesn't really matter what input comes from this side, right? If it's a 0 here, the output will obviously be 1, right? The output will obviously be 1, okay? And that 1 will be carried out to here, okay? It will get carried out to here, and now we have 1 and 1 as the 2 inputs for this gate, right? For this gate, we have 1 and 1. If it has 1 and 1, what should be the output? it should be 0, right? So we put 0. Okay, and that 0 actually travels up here. Again, we have 0 and 0. Just to check, 0 and 0 does give out 1. Did you understand what happened here? Huh? The outputs came in as 1 for Q, 0 for Q bar. Right? Now, look at it again. I'm going to teach you that again. Because you understand this simple part, you are going to be like totally okay with all the types of flip-flops. Right. Now what I did was I just gave 2 random inputs. Right? They were actually random. Right? I just gave 0 here and 1 here. Right? So as I told you, as long as there's 0 on one of the inputs in an AND gate, as long as there's a 0 on one of the inputs of an AND gate, the answer will be 1. Right? The answer will be 1. Answer will be right? So we just put 1 there. It doesn't really matter what comes out of here. Why? Because at the end of the day, if S is 0, the answer should be 1. That's the logic that we came up from here. Right? Should be 1. That 1 actually travels down to here. Travels down to here. Right? We have 1, 1. If we have 2 1s, the answer is 0. And that 0 travels up. 0 and 0 is actually equals to 1. So it's like we just confirmed that it was true. Right? That's what happened. We just moved along. Right? As I said, S means set and R means reset. Right? So what we're going to do is we always start with set and ends on reset. Right? We try to start with set. Right? We just try to start with set. So we started from here. Sometimes we'll start with R as well. Right? We'll talk about those situations later on. But just remember that we usually start from set. Okay? Doesn't matter if S is here or S is here, we start from set. If S is down here, we're going to start from down and move up. Right? What happened this time was we started from up and moved downwards. Right? We can move upwards as well. It's totally okay. Alright? Cool. So I put 0 and 1 and this happened. Then what I'm going to do is I'm going to put, I don't know, 1 and 1. 1 and 1. Okay? Let's see what happens. Now here's the thing. Now Q and Q bar already has an output. Right? And as I said, in flip-flops, they can remember 1 bit. Okay? They can remember 1 bit. Now there are essentially 4 bits written here. Maybe repetitions, right? We have 4 bits written here. Out of these 4 bits, which are the bits, which bit will be saved? Obviously not the inputs, right? Because the inputs just changed. Alright? The inputs just changed. The inputs just changed to 1 and 1. Right? What they remembered was actually Q. Right? Now you might think, no, both Q and Q bar must be saved here. Not really, right? If you remember Q, Q bar is supposed to be the inverse of that. Right? Whatever Q is, Q bar is supposed to be the quite opposite of it. Right? So that's what happens. We have Q, then we have Q bar. So if the flip-flop can remember Q, it means essentially it's remembering Q bar as well. Get it? It's just remembering Q bar as well. Right? Now in this scenario, we are stuck with this. Right? When the new inputs are given, we already had the past outputs. Right? So it's a bit easier this time. Why? We're going to start with S. As I said, okay, it's always set, reset. We can't reset anything unless we set it first. Right? So remember that we always move to the set first. Okay? So set 1 and 0. 1 and 0, it equals to 1. Okay, it's the same. That 1 down, move down here. Then we have 1 and 1, which is 0, right? 0 moves up here, 1 and 0, and it's the same thing, right? And it just goes as a loop, right? It just goes as a loop. So, did the outputs really change? No, right? I didn't even erase this once. They actually didn't change, right? The outputs remained as 1 and 0. Okay, it remained as 1 and 0, right? All right. Next up, let's do 1 0. Yeah, sure. Let's do 1 0. I don't know. So this time I'm going to keep 1 here, and I'm going to do a 0 here. Wait, red pen. Yeah, I hope you all are like still with me on this. Okay, this is kind of complex. That's why we are having a separate seminar for this. Yeah, so we are keeping 1 here, 1 for S, and 0 for R, right? Let's again start from S. Okay, we're going to start from S. S, we have 0 and 1. If it's 0 and 1, it means the answer is 1, right? And that 1 goes on to here. Okay, 1 and 0 is actually 1, right? 1 and 0 is 1. Finally we are changing an output. And if you noticed, like both the previous times, what I did was I started from S, went down to R, and actually again moved up to S as well. So I'm not going to stop here. I'm going to take this 1 to here. Okay, I'm going to take it there, and I'm going to run this NAND gate again, right? I'm going to run this NAND gate again, 1 and 1. The answer is 0, right? The answer is 0, it's not 1. Turns out we had to change both of them. And that 0 moves down to here. We are going to go round and round until we get to a proper output. Okay? 0 and 0 is 1. 1 goes here, 1 and 1 is 0, and that's perfect, right? If it's not Lamai, we'll have to move again and again and again and again. Okay? So what happened this time? We started with S, we went down to R, we went back to S, and we went back to R as well, right? So we moved 1, 2, 3 times, right? Yeah, 3 times. Okay? We started from up, moved down or something, right? I'm going to put 1 and 1 again. Right, we have 1 and 1. Here, we have 1, 1, which is 0. 0 moves down to here. 0 and 1 is 1. That's right there. That 1 moves to here. Again 1 and 1, 0. Alright, okay. Yeah, it works perfectly here. So did the outputs change, Lamai? Did the outputs change? No, they didn't change. So the outputs remained as 0 and 1. Okay, 0 and 1. Next up, finally, I'm just going to put 0 and 0. Okay, I'm just going to put 0 and 0 and see what happens. We have 0, 0. Okay, this 0, like because of this 0, Q turns into 1. That 1 moves to here. Again, because of that 0, this moves to 1 as well. This will remain as 1. Okay, and that one will go on to here, 1 1. The output is 1 1. There's a huge issue here because Q and Q bar cannot be the same lemma. It cannot, right? It cannot be the same, so it doesn't really work. Okay, doesn't really work, right? Now here are the things that you need to focus on in NAND gates. Sorry, in NAND flip-flops. Right. I'm just going to draw the final truth table. Right. Here's the truth table. It looks a bit weird. You'll see why. We have S, R, Q, and Q bar. Okay? Right. We have our usual inputs 0, 1, 0, 1, 0, 0, 1, 1. Okay? So what happened when there were two zeros? When there were two zeros, Lamai, the outputs came as 1 and 1, right? As I said, both the Q and Q bar cannot be the same. So, it's actually an invalid thing. It's invalid. We just write invalid. Okay? Next up, what happened whenever we had 0 and 1? The outputs were 1 and 0. Okay? What happened when the inputs were 1 and 0? Like this. The outputs were 0 and 1. Finally, what happened when the inputs were 1 and 1? Actually, there were two possible outputs for that. Right? There were two possible outputs. And actually, those outputs are the same as the previous outputs. See, nothing really changed. These two went down to here, and these two remained the same and went down to here, right? So whenever the inputs are 1 and 1 in this specific flip-flop, not in any flip-flop, in this specific flip-flop, the answer will be the same as last. It will be the same as last. Kalin tibba output ekama thamai මේ සැරේ output එකටත් එන්නේ. Get it? So this is the SR NAND flip-flop. I hope you all actually understood how this happened, how this entire thing happened, and how we had to like put inputs, start from the set all the time, right? You know what, I'll just put some pointers around here. Start from set always. Do not stop till the flow is stable. Do not stop till the flow is stable. right? Number 3, Q and Q bar cannot be same. The reason why they cannot be the same is, number 1, it's common sense, right? Q and Q bar cannot be the same. But at the other hand, it's always that the flip-flop remembers Q. It doesn't know who Q bar is, right? It remembers Q, and what it does is it just inverts the answer and put it to Q bar, right? So that's what happens. So at no point ever can both these be the same answer. Okay, right? So yeah, so these are invalid input. We can't put 0 and 0 in a NAND flip-flop, right? If we put 0 and 1, output, output, and if we put 1 and 1, the output will be the same as the last output. Okay, hope you all understood. If you all have any questions, send me a text as soon as possible. And yeah, I'll give you all like 5 minutes to put this down. Cool? Right, okay, enough time. So what I'm going to do is I'm going to connect the synchronous part or the clock latch part right to this here. Okay, hear me out. Now we have this, right, and we got this. Okay, I'm going to erase all the other parts and only keep this truth table here. Okay, because I'm going to have to draw a whole new logical circuit. Hope you all remember this though. Anytime there's a 0, the output is 1. Alright, let me keep the rules as well, it's fine. And remove the arrow. Okay. First, you all should know what a clock is. Right? I'm not quite sure if everyone knows what a clock is. Right? Lamai, in the most basic sense, a clock is a clock. Right? It ticks. It ticks 1 and 0, 1, 0, 1, 0, 1, 0, 1, 0. It's an internal clock that works inside the computer to tell the CPU actually no, a clock is there to keep everything synchronized, right? Everything synchronized, that's inside the CPU, right? And that's how many times a CPU can do an instruction in a given second, right? Now, I checked yesterday actually for a class that my laptop's CPU speed or my laptop's clock speed is actually at, oh god, I just forgot. Is actually at 4. I think it was 4.5 gigahertz, 4.4, 4.5, right? 4.5 gigahertz, meaning my clock ticks around 4.5 billion times a second. It's not a small amount, right? It ticks a lot. Okay, that's what happens in a clock, right? The clock goes to 1 and 0 alternatively, right? Alternate maybe yana 1 and 0 volt, right? Now what we are going to do is we are going to add 2 gates and the clock bit to our normal logical circuit, right? Okay, so let's see how this is going to be drawn. Okay. Hold on, be patient while I'm drawing this. Like there's a lot to draw here. So yeah, there are 4 NAND gates here. Okay, there are 4 NAND gates here, and I'm still not done. We have the S input coming all the way from here. We have the R input coming from around here, and on the middle actually connecting to both of these is the clock. Okay, this is the NAND flip-flop with the clock. Alright, this is the NAND flip-flop with the clock. I hope all the small circles on the NAND gates are visible right here, here, here and here, right? If not, just imagine they're there. They are. I don't know if you can see this. Right. Here's the only thing that you all have to remember. The clock can be either 0 or 1. Right? 0 or 1. Okay? Now what happens is that 0 or 1 actually changes all the time. Right? It changes. Right? 0, 1, 0, 1, 0, 1, change. Right? Now our job is to learn what happens when the clock goes to 0 and what happens when the clock comes to 1. Right? So let's start with what happens when the clock goes to 0. When the clock goes to 0, right, this will be 0 and this will be 0. As we know, 0 here is 1 here and 1 here. I honestly forgot the most important part. I can sense that my WhatsApp is full of messages right now. Normally whenever I make some kind of a small mistake in a class, everyone hurries into their WhatsApp and just sends the text. Right. Here's what happens. 1 and 1. Okay. If these two are 1s, is there any way that... Oh wait, sorry. Okay. If these two are 1s, doesn't it actually means that this happens? Right? Now, this was the last part that we, like, I'm gonna mark this part in dashed lines, right? Because this was the part that we just finished learning, right? Now this squared part is the part we were talking about, right? This is the normal flip-flop or the normal latch, right? If both inputs are 1 to these two, right? If both inputs are 1, we already know what happens, right? We already know. We don't need the answers for these. We don't need anything else. We already know if both inputs are 1, whatever happens, it's the same output as the last. Get it? Huh? So the clock gave 0. Because the clock gave 0, both these NAND gates gave out the answer as 1 because there was a 0, right? 0 එක තිබ්බ නිසා 1 ආවා. If both are 1, it means the output remains as the last, right? It will be the same as last. So here's the point to remember. When the clock is 0, the output does not change. Get it? Huh? When the clock is 0, the output doesn't change, right? Why? Because both the inputs are 1 and 1, and we know if they are 1 and 1, it will be the same as last, right? So as long as the clock is 0, our flip-flop doesn't do any damn thing, right? A flip-flop doesn't do anything, right? It's just closed. You can pause it out at the end. Like pause it out. Yeah, you can pause it at the end. That's what happens, right? But now imagine the clock is 1, right? Clock is 1. Now what happens is, if the clock is 1, it can't really give an output only based on the clock input, right? These two logic gates can't give an output only based on one input. So they'll obviously have to take S and R as well, right? They'll have to take S and R as well, right? And with that, our entire logic circuit or flip-flop. But when the clock is 1, the output can be changed. I'm not saying that it will be changed fully. It can be changed. Basically, Namai, if the clock is 0, our main flip-flop area gets locked. Like a lock window, right? Gate to adala lock kala wage. Hari, it doesn't work. It's paused. But if the clock is 1, it means it's unlocked. It can work as usual, right? So if the clock is 0, the flip-flop is actually paused. And if the clock is 1, the flip-flop works as usual. Okay? Those are the 2 points to get from there. Cool? I think it's cool because like it's not the hardest thing ever. Right. Let's get to writing these parts as well. This really remains the same. It doesn't change. It's just these 2 points. Right? Draw these two, and get finished with it. Again, if you all have any questions, just ask me through WhatsApp. Like right now would be better, so I can answer like to all of you at once. All right, let's move on. Sorry, it took some time. We're going to move on to R is no flip-flops, right? So we're going to change the entire thing now. We're going to start with R is no flip-flops. I know this took a while. I know this took around 1 hour and 15 minutes. Wow, I didn't think we'll take that much time. Anyways, this part will actually not take a lot of time, right? Because I'm not going to waste a lot of time teaching y'all here. Instead, we are just going to like straight up move to it. I'll just keep the rules here. Right. Next topic is the R is no flip-flop. R is no flip-flop. Okay? Right. The R is no flip-flop lamai. It's actually the same as the NAND flip-flop. Instead of NAND gates, we have no gates. We have our two inputs. And the two inputs will not go as R and S, they'll be going as, S and R, they'll be going as R and S this time. That's the difference, right? That's why we call it the RS flip-flop. Okay? We call it the RS flip-flop. We changed the S and R, but we're going to keep Q and Q bar as they are. These two don't change, right? Q will be on top and Q bar will be on the bottom. All right? Cool. So again, just like before, what I'm going to do is I'm going to draw the truth table for a normal NOR gate. And let's see what kind of a logic we can get out of this. Okay? We have A and B. We have A, B, I'm sorry, it's just it's A plus B over bar, right? These are the inputs and the outputs are as follows. This becomes 1, this becomes zeros. It's the opposite of an OR gate. Ne? I don't have to teach you, I don't think. Right? So here's how it goes. 1 and 3 zeros. Look at this. Get some kind of a logic out of it. Alright? Till I draw this table. Sorry, it's R and S. Okay, So what's the logic that you got out of this? The logic should be that whenever there's a 1, the output is 0, right? Whenever there's an input 1, the output is 0, okay? Whenever there's an input 1, the output will be 0. That's the main logic here, all right? So we're going to use that logic, and we'll start with, I don't know, 1 and 0, right? We'll start here. Yeah, why the hell not? Shall we? Yeah, we'll actually start with this and see how the outputs goes. This was 1, this is 0. As I said before, like 3-4 times, even though S is on, like S is down here, we always start with S, okay? We're going to start with S. Alright, so we start with S. 1 against start column. If there's a 1 somewhere, the output should be 0. That 0 goes to here. 0, 0 is 1. That 1 comes here. 1, 1 is 0. See, it works. So Q will be 1 and Q bar will be 0. Next up, let's try, I don't know, 0 and 1. No, 0 and 0 now. Yeah, 0 and 0. Okay. I'll change this into 0 as well. So we can start with 0. 0 and 1, it's 0. 0 goes here. 0, 0 is 1. 1 goes here. Again, it remains the same. So the answer didn't change. You already know what that means, right? Then we have 0 and 1. So R becomes 1 now. R becomes 1. If 0 is here and 1 is here, the answer is 0. 0 moves here. 1, 0. Q actually becomes 0. Right? This becomes 0. That 0 goes down here. 0, 0 is 1. 0, 0 is 1. Get it? That's what happens. So this time Q is 0 and Q bar is 1. We'll try 0, 0 again just to see if we get the same outputs. Now again 0 and 0 is 1. 1 moves to here. 1 and 0 is okay, never mind. Right. 1 and 0 here. If it's 1 and 0, it remains as 0. Right? That's what happens. It remains the same. Right? Finally, let's try 1 and 1. We have 1 here, meaning 0 here. The 0, sorry, we have 1 here, meaning 0 here. That 0 goes to here, 0, right? Both Q and Q bar are 0. Meaning, if we draw the proper truth table for the no flip-flop, it will look something like this. So this is S, this is R, this is Q, and this is Q bar. Right. So this time, when it's 0 and 0, the output remains the same as last. When it's 0 and 1, outputs are 0 and 1 as well. When it's 1 and 0, 1 and 0. When it's both 1 and 1, it gives us the same output, meaning it is an invalid state. See, it's essentially the same thing that we talked for the NAND flip-flop, right? It's essentially the same. Okay? එක වගේම කතාවක් තමයි තියෙන්නේ අපිට කරන්න. හරි? Right. So this is the no flip-flop. I hope you guys understood, because like there's nothing new to talk about here, right? It's the same things that we did in the NAND flip-flops. All right. Again, take like 5 minutes and put this down. After that, we'll move on to the last bit and finish today's class. Right. Okay, Lamai. So for the no gate, we're actually not going to connect the clock bit, right? We're not going to connect the clock bit. The clock bit usually only gets connected to the NAND SR flip-flop, right? Not the RS1. Okay. So with that, we've actually come to the end of the class, right? This went on for like exactly 1 hour and 30 minutes from my side. For y'all, it'll be around 1 hour and 28. I don't know. Actually, don't know. Right. Anyways, for like 1.5 hours, I actually hope that y'all really understood what I was like trying to tell y'all, and understood how these actually work, right? Because even for your A-levels, the exam board or the paper board have started giving flip-flop questions, right? They didn't till like 2023, and starting 2023 they are actually putting some more flip-flop questions in. Okay, so learn this. We'll meet in the papers again. Like for these parts, we'll meet in the papers again, and the next seminar will be on this Sunday, 28th Sunday, and it will be on e-commerce, right? We're going to do the entire lesson of e-commerce. Sorry, it's not e-commerce. Is it e-commerce? No, it's not e-commerce. It was artificial intelligence, right? It's AI and future trends. We're going to do the entire lesson. And yeah, I'll see y'all then. Bye bye. See ya.